energy equation, the first law, the first law of thermodynamics, and this begins in your textbook on page 251. This is really one of my favorite sections in this entire textbook. The reason is it brings together a whole lot of different ideas. We talk about the first law of thermodynamics, which of course we've studied in physics and thermodynamics and maybe in chemistry. We also talk about energy, which is something that we've talked about in dynamics and physics. And we're bringing it together with some topics, not really topics, I would say techniques that we've begun using, like the material derivative and the Reynolds transport theorem, and brought all of these ideas together. So this is a great section. I'm not going to go through the derivation. I'm going to put them up on the board or on the camera so that you can see them. And then we're going to talk a little bit about units and actually applying these equations. So this is a chapter where we are synthesizing or bringing together a whole bunch of different ideas, or really maybe just a few ideas from a whole bunch of different fields of study. So let's get started. In your textbook here on page 251, you see that we have the first law of thermodynamics. And for those of you who have not ever seen it before, which I think most of you probably have, but the first law of thermodynamics, which I abbreviated like this, thermodynamics first law, states that energy in all of its forms is conserved. Now, strictly speaking, that should be specified in the absence of a nuclear reaction. And if you have a nuclear reaction, you have some mass that is becoming energy, but in that particular case, you can still account for it. You just have to use Einstein's law, which just says that energy is equal to mass times the speed of light squared. So essentially what that's saying is that a wee tiny amount of mass, because this is a huge number, when we take it to the second power, results in, if you can take a tiny amount of mass and change it into a large amount of energy. There's other things that it means as well, but that's one of the things that we're talking about. But basically, the first law of thermodynamics for a system, then, is, as it says here, the time rate of increase of the total stored energy is equal to the net time rate of energy addition by heat transfer and the net time rate of energy addition by work transfer. And so basically we have the material derivative stated here, where we have a change of energy, little e, that's intensive E, so that would be analogous to little b in the material derivative, or in the Reynolds transport theorem, of the system is equal to Q, one of the most overused variables, right? Here it means heat, can also mean volumetric flow rate, but Q dot is going to be a rate of heat addition, Q dot out, a rate of heat removal from the system, plus the rate at which work goes into the system, minus the rate at which work goes out of the system. And it simplifies to the material derivative ddt of the system integral little e rho dv equals q dot net in, so that's just taking into account the ins and outs and the work net. All right, now for a mechanical system, the little e, or the energy of a system, can be U, internal energy, plus V squared over 2, kinetic energy, plus GZ squared, or GZ, sorry, no square. And so this is potential energy, kinetic energy, internal energy. All right, so we continue and we're still working with the material derivative Reynolds transport theorem as we get down here to equation 558. Now, there's something really interesting that happens here. This equation can be found, we can find this equation that discusses this equality of heat, work, and energy. Or we can find it using the Reynolds transport theorem, we can find it using the material derivative, and we can find exactly the same thing working in more mechanical ways. So here we talk about W dot of a shaft, which is the torque of the shaft times omega, omega being the angular velocity. We can check units on this if you want, but I want to go through this a little bit and talk about what W dot, what Q dot, and so forth will yield. So here we have a fluid pressure equating to a normal stress, which we had done in a different form back in Chapter 1. And we can just talk about the sections of the pipe. So really, we are coming up with these ideas that all come back to the same place, which is this equation for total stored energy. Now, there's a couple of things I'd like you to see. After we go through this, we have a pressure over rho, V squared over 2, and we have a GZ term. These three terms are what we see in one form or another in the Bernoulli equation. Does that look familiar to you? Now we have added in this internal energy term because we have to take into account the state of the fluid in terms of its temperature, its pressure, and so forth. But really, we're coming up with something from this very mathematical material derivative Reynolds transport theorem point of view that starts to look a lot like Bernoulli, which we came at from an entirely different angle. Now, that is a very satisfying conclusion, or correlation at least, because when we're working with fluid properties, when we're working with anything in the physical world, we should keep coming out with the same ideas. There are very few ideas, and they apply all the time. Meaning, when I say ideas, what I'm talking about are laws. And the conservation of energy, or the first law of thermodynamics, should all lead us back to the same spot. And it does. So that's kind of cool. So anyway, the rest of this chapter just talks, or not the rest of this chapter, but in large part we continue discussing this same idea, energy conservation, and we talk about, we've added in this idea of internal energy, which those of you who've been in thermodynamics have seen. But let's talk about a couple of different terms and what the units look like. Q dot is rate of heat transfer. If it's in, it increases the energy of a system. If it's out, it decreases the energy of a system. The rate of heat in or out. So I could call it transfer. W dot is work rate. I will have to say rate of work, in or out. And that is referred to as power. We have little u, which is internal energy. And also we have pressure and velocity and energy of position, right? So pressure over density is pressure energy, I guess I would say. I'd like to define this a little bit differently. If we take G times Z and we divide that by G, that will give us Z, and that will give us elevation head. So to keep these terms analogous, we have a kinetic energy term of V squared over 2. If we divide that by G, we'll get something that will have dimensions of length. We can call that velocity head or kinetic energy head. And similarly, if we take P and divide it by rho G, that's the same as P divided by gamma, right? Not rho, that's P divided by gamma, and that's called pressure head, right? So when we start working with these Bernoulli-like terms, we also need to be very, very careful to make sure that our dimensions and our units work out properly. Now, internal energy plus pressure times specific volume is a term called enthalpy. Ugh, not spelled today. E-N-T-H-A-L-P-Y, right? And so we could also say that we refer to that as little h, okay? Little h is equal to U plus P over rho in a different set of units, okay? And that is, we can check out what the units will look like in just a minute, but U is generally going to be in energy per mass, and energy can be measured in foot-pounds of force, or it can be measured in Newton meters, for example. So if you look at pressure over rho, pressure is in the metric system Newton per meter squared, right, Pascal, and rho is a density term, so that is going to be in mass per volume. Okay, so if you take a look at this, you get Newton is a kilogram meter per second squared, and mass would be measured in kilograms. Volume would be measured in meters to the third. So if you get kilogram per second squared meter squared, where do we go with that? Well, we'll discuss that, and we'll get to that answer in just a moment. Newton meter per kilogram. Let's try that. Okay, that looks a little bit better. And a Newton, let's do this. A Newton is a kilogram meter per second squared. So then density, which is in mass, kilograms per volume, meter to the third. Okay, there we go. So we'll finish off that discussion in just a second. All right, well, continuing with the idea of energy being conserved. If energy is conserved, it's only going to change forms. The most useful form of the equation at this point is going to be, if we take a mass flow rate and we multiply it by the terms associated with the fluid, enthalpy out, enthalpy in, velocity out squared, velocity in squared over 2 plus g times the elevation on the outlet minus the elevation on the inlet. It's going to equal what we add or subtract in terms of heat and rate of work or power. So what this form of the equation allows us to do is not only to have a system that is not perfectly insulated, but also to have a turbine or to have line loss, which is something that we hadn't really talked about with Bernoulli. But anytime that you put fluid through a pipe, there's going to be a frictional contact at the surface of the pipe. And so we're going to have some work that goes in, or some power, the way that we have this phrase, but we're also going to have some loss in terms of what's going on with the contact between the fluid and the surface of the pipe. And so you can put in work with a pump. You can remove energy in the form of friction, and we can take all of those things into account using this form of the equation. Now, there's another useful form of the equation. I'm going to flip over here to the book again. Here in section 5.3.3, you'll see that we have P out over rho plus V out squared over 2 plus GZ out. So we have the out terms. We have the in terms, which once again, this looks very much like Bernoulli. But then we also have internal energies in and out, and we have some sort of a Q net in. This form of the equation, 5.72, is written in terms of m dot, or in terms of an extensive property. This form is written by dividing m dot out. That's why these variables become small, and the dot, or the rate with respect to time, go away. So everything here has been divided by m dot. And what happens in that case is we are working with intensive properties. And the thing I wish to point out to you is just how similar this is to the Bernoulli equation. When we get down here, we have something in terms of pressure units that is essentially identical to the Bernoulli equation. Okay. Now, something that will happen at this point is that when we start talking about these losses, we can quantify them. Sometimes a U in, a U out, a Q net in is very difficult to quantify, but we can call it a loss. And a lot of times if you have a pipe, depending on the roughness of the pipe or the type of a pipe or the type of an appliance, it doesn't even have to be a pipe, it can be a turbine, it can be any conduit at all, that you can quantify based on the frictional properties of that conduit what the losses are going to look like. And you can do the same for gains. When you have a pump, for example, you may notice that a pump is rated as so many horsepower. That is actually a power, or a W dot, that you can put into the system. So if you know something about the quality of the pipe, the quality of the friction between the fluid and the pipe, and you know something about the rating of a pump, you can use the Bernoulli equation to express those ideas in terms of a relatively simple equation. And the rest of these, we have some examples of what those are going to look like. All right, now there's a form of the equation in your textbook on page 262. That is a combination of this very theoretical hydrodynamic approach and this very hydraulic, hands-on empirical approach that gives you an extremely useful working form of the first law of thermodynamics. And we look at the outlets, so you can see that we are kind of looking at a Reynolds transport idea. In other words, we're relating what's going in and out of a system, or excuse me, I should say in and out of a control volume. And we have these all very Bernoulli-looking equations. To this point, we're kind of identical to Bernoulli, aren't we? But then we can add to that the work. This is small w, or intensive work, that we have from some sort of a shaft, and the losses. And as long as we keep the losses and the work in the same units as these terms, the same dimensions as those terms, we have a dimensionally homogeneous equation. And we can use it just like we use the Bernoulli equation to really quantify the mechanical energy of the system. Now here, getting back to the idea of the units that we talked about, we know that pressure, you can just take any of these terms. Well, this is actually the easiest one to work with. Since V, velocity, is in units of meter per second or feet per second, we can see that this term is going to be in units of meters squared per second squared or feet squared per second squared. In other words, in dimensions of length squared per time squared. So we can bet that each of these terms is also going to be in dimensions of length squared per time squared. So let's just check. G is in length, that's the gravitational constant, right? Length per time squared, the acceleration. Z is length. So we can see that the dimensions of this term is length squared per time squared. And similarly here, pressure is in, say, newtons per meter squared, and density is in kilograms per meter cubed. But a newton, in order to get this in terms of, well, we could do it either way, but let's just say a newton is a kilogram meter per second squared. So we've got that per meter squared. And then we have a kilogram per meter to the third. So we have kilogram squared, this meter cancels one of these, per second squared meter to the fourth. And how does that become a length per time squared? In other words, is this equal to length squared? Because we have a second squared right here. Okay. It doesn't look that way, right? Does it? So is this term, do we have an analogous term here? Density. If we take a look at the front cover of your book, the density is in, that's kilogram per meters cubed, right? So this is not working out as far as I can tell. Oh, because this is in the denominator. That's what I'm doing wrong. So density is, if I do it in terms of metric or SI units, my density is in kilogram per meter cubed, but it's in the bottom. So kilogram per meter cubed. That's better, isn't it? So that cancels that. Newton is a kilogram meter per second squared. And I'm still left here with a meter and with a kilogram. So my kilograms cancel out, and I get meter squared per second squared, which is dimensions of length squared per time squared, which is analogous to that. So once again, that's just a basic algebra problem. When you divide, you have to reciprocate and multiply instead of just multiply, which I think we all knew that before we came in. I just sort of momentarily decided it wasn't true. So, but it still is the good news. All right, so now that we know that we have dimensional homogeneity, we can write the equation in terms of units of length or head. And this is in your textbook on page 264. And this is an extremely useful form of the equation. Equation 5.84 on page 264. So if we take a look at the document, Cam, we can say this has come about from RTT, from the material derivative, from the first law of thermodynamics, and from Bernoulli. That P out over gamma plus velocity squared out over 2g plus z out equals P in over gamma plus b squared in over 2g plus z in, which at that point is identical to the Bernoulli equation written in dimensions of length plus h sub s, which is a head gain or head due to work coming in from a shaft. So that would be W shaft net in divided by g in order to resolve the dimensions minus head loss, which would be in feet as well. Right. So this brings us to a really interesting place where we have found the same piece of information or the same relationship over and over again through very theoretical methods and also through very hands-on methods. And whenever that happens, it tends to indicate that what you're doing has general applicability. So the equation that we came up with, 5.84, is a highly adaptive, and in one way you can look at it as just being an adaptation of the Bernoulli equation. You could say, okay, well, here's my energy that went out, here's my energy that went in, and if there's any changes, it either had to be added or lost from that system. So you can look at it in that simple form, or you can think about it in a more complicated way. But in any case, it's a universally applicable or nearly universally applicable form of the equation. Very, very useful. So the problem that I would like to look at in terms of applying this and also looking at those dimensions a little bit is problem 5107 in your textbook. And 5107 is here on page 293. So 5107. I also like this because since we're talking about energy in terms of feet, what are we getting at? We are talking about taking energy of water and projecting it some number of feet into the air from a fire hydrant. So we have mass balance going on. We have energy moving from one form to the next. And so we're not going to do this in terms of momentum methods. We could, but it would be a lot more complicated because of the vector nature. But we'll just talk about energy, and we'll talk about sort of this ginned up Bernoulli or derivation of the, or not derivation really, but a derivation from the Reynolds transport theorem, equation 584. All right, so what do we have? We have a pumper truck, and it's to deliver 1.5 cubic feet per second. That would be a volumetric flow rate. Q is equal to 1.5 cubic feet per second to a maximum elevation, Z, of 60 feet above the hydrant. The pressure at the 4-inch diameter outlet of the hydrant, 4-inch diameter hydrant, the pressure at that point is 10 psi. So the pressure at the hydrant is 10 psi. Now, if head losses are negligibly small, that means H sub L is approximately equal to 0. Determine the power. So we want some sort of a W dot. How much power are we going to have to put through the pump in order to squirt the water up that high? All right, so I've written down a few of the variables here. Q is 1.5 cubic feet per second. Z is 60 feet. We have a 4-inch diameter hydrant, and the pressure at the hydrant is 10 psi. Our head losses are 0, and we wish to know what our W dot is. All right, so we can look at this in terms of all of these terms that we have written down here. This is what we're getting at. This is what we wish to solve for. We'll have to get it into some form that has acceptable units, but we're told that this is equal to 0. If we consider what's going on here, if we call this the outlet, what we're trying to get is this 60 feet in the air. The pressure here is atmospheric. The velocity here, what's going to happen at the maximum velocity? Once again, you can the maximum height. You can come up with this thinking about kinetic equations, the kinematic equations. When you reach the maximum height of an arc, the velocity here is equal to 0. That's what makes it be the maximum height. If there was velocity left, it would continue to increase. But if we're looking at this as being the outlet, we want to reach a height of 60 feet. We have some sort of a pressure. We have some sort of a velocity. And we have some sort of a Z of that inlet. Well, one thing we can think of is if this is the hydrant and this is 60 feet above, we can consider that to be 0, just because Z2 minus Z1 is 0. The hydrant isn't really at a Z is 0, but we're using that as our datum. All right, so we can rewrite this equation. I'm just going to simplify it. Z2 then will be equal to P1, or P at the hydrant, divided by gamma. It's actually going to be rho, isn't it? I don't know why I have gamma there. That makes the units come out properly. Just remember gamma is equal to rho times G. Plus V squared over 2G, that's 0, plus H sub S. Okay? Or we can say then that Z2, or delta Z is what it really is, minus P1 over rho minus v squared over 2g is equal to h sub s. And that's going to be the value of the power in feet, and then we're going to have to turn it into some sort of a power at the shaft or pump power. All right, so if we write that equation, then we know that Z2 is equal to 60 feet. We know that our pressure at the pump is 10 psi, which is pound of force per inch squared. So we're obviously going to have to do a conversion with that. There's 144 inches squared per feet squared, right? And then we have rho of water, which is 62.4 pounds per cubic foot, right? And then we have to talk about what's going on with the velocity of the water. We're going to have to work with that a little bit, aren't we? So let's talk about velocity. We're given a Q, a flow rate. Q is equal to 1.5 cubic feet per second. We know that Q is equal to velocity times area, and we know that our area on the hydrant is 4-inch diameter. So the area is pi times d, 4 inches squared over 4. And then once again, we're going to have to convert that because there are 12 inches per foot. So that's 144 inches squared per foot squared. And if I do that, then I can find my velocity. I'm just going to write this down. I know my Q, 1.5 cubic feet per second equals velocity divided by this value of area, which I want to compute just because it's kind of a messy number at this point. All right, so we have pi 3.1416 times 4 divided by 4. So one of these 4's will cancel one of these 4's, right? So I can just take 3.1416 and multiply it by 4. And then to get it from inches squared to feet squared, I can divide that number by 144, and I get that value is 0.08726 in units of feet squared. So the area of the outlet was actually the inlet for this problem, but the outlet of the hydrant is 0.08726 feet squared. 0.08726 feet squared. Feet cubed cancels to feet against this. So if I take 1.5 and divide it by that value, I'm not used to using this calculator. Take 1 over that number and multiply it by 1.5. I get that my velocity of the water coming out of the hydrant is 1.79 feet per second. I said 1.79, it's 17.19 feet per second. All right, so what that means is that that's the value that's going to go into this equation right at this point. All right, so continuing then, all of my units are resolved. It's going to be minus 17.19 feet per second squared over 2g. G in the SI system would be 9.8 meters per second squared. In US is 32.2 feet per second squared. All right, and so those are my terms. So I have 60 feet, this is going to be h sub s, 60 feet minus, let's go ahead and run these numbers, 10 times 144 divided by 62.4 . And that value comes out to be 23.077. I'm carrying way too many decimal places at this point. But I have pounds, pounds, inches, inches, feet squared, feet to the third in the denominator becomes feet. So this number is 23.077 feet. And then last but not least, I subtract this value 17.19 divided by 2 divided again by 32.2, and that value is 0.267 feet squared becomes feet. Second squared cancels out. This cancels against one of those, and that's in feet. So my H sub S, or what I need to add from the pump, is 60 minus 23.077 minus 0.267, and I need to have a head gain from my pump of 36.656 feet. Okay, now once again, this number is, oh, this has to be squared. All right, I have a little problem here. Let me get this again. 17.19 squared divided by 2 and divided again by 32.2. Okay, so this number is not this. It's 4.588 feet. So this value is 60 minus 23.077 minus 4.588, and that's a value of 32.335 feet. All right, so I need to gain 32.335 feet. How do I turn that into a W dot term? Okay, because this is correct, but what kind of a unit do I want? Well, a good unit for power from a pump in the English system is horsepower. And if we take gamma times Q times H sub S, gamma being the weight of water, 62.4 pounds per cubic feet, and multiplying that by the Q, which is 1.5 cubic feet per second, and multiplying that by the feet that I need to gain, 32.335 feet, I get a value of 62.4 times 1.5 times 32.335, which is 3,026.556. What are my units? Well, feet cube, or feet cube, right? So I have foot pounds. So there's a foot here, foot pounds per second. All right. Now, continuing with this idea, the conversion between foot pounds per second and horsepower is, you can look this up in your book, 550. So 550 foot pounds per second is equal to 1 horsepower. So I'm going to say 1 horsepower per 550 foot pounds per second. Cancel, cancel. So if I take that number and I divide it by 550, I get what I need out of my pump, which is 5.5 horsepower. All right. So in a real world, you would probably want to get a pump that's rated at higher than 5.5 horsepower. If you had a 10 horsepower pump, you would be well on your way to being able to lift 1.5 cubic feet per second of water to a height of 60 feet. Now, a big assumption in this is that we did not have any losses. We were told that the head losses were negligibly small, so in most cases the H sub L term would not be negligible, and we would have to take it into account. I think it's kind of unrealistic to say it would be, because if you're going through a hose, you're going through a hydrant, there's going to be a lot of places to lose head. So if I were really designing this, I would definitely, if it called out for a 5.5 horsepower pump, definitely think 10 would not be too big. All right, so that's it for this section. That's it for this chapter. We're not going to cover section 5.4, so we're done with chapter 5. So your homework is posted to our Moodle site. And if you work the problems, then let me know when you have questions and problems. And next time I'll see you back for chapter 6. See you then.